Hello, and welcome to my talk about the entity component system and how we use it in Skylines II. So I will start introducing myself. My name is Damien Morello, and I have worked in the game industry for about 20 years now, actually over 20 years. And out of which 14 I've been at Colossal Order. So I've been there for a while, and I've seen the previous title in development as well. And I work alongside with 10 to 11 other programmers, which are very talented and in the tech department. And that's about it about me. So today we're going to talk about City Skylines and how we use Unity in its current state and what ecosystems worked for us and how we integrated them. So City Skylines 2, for those who may not know about it, is a city builder, just like the first one. It was released at the end of last year, around October. And so it's soon a one-year birthday. And it provided a large-scale sandbox, which focuses on providing player freedom. The idea is the player should be able to do anything he wants, and we try not to set any arbitrary limitation by design so that they can get very creative. And the first game, Skylines 1, we used dedicated threads to make the simulation work, and with a heavy use of non-managed structures, we eventually got the performances to a pretty good place, and the game shipped and has been quite successful. But the truth is, with modern hardware, where you want to scale up the simulation with the amount of cores that are available on your machine, you need a proper multi-threaded solution where you can really implement a lot more details. So at the time, we wanted to build a game that is similar to the first game, but with a lot more details, bigger scale, and kind of better everything. So we ended up looking a bit at Unity State, and ECS, nobody knows as entities package, was just coming up. It was very fresh, very new, and people were excited about it, and so were we. So we felt it was going to be a good match, and we adopted ECS from early in the development. So as marketing puts it, with deep simulation and a living economy, City Skylines 2 is world building without limits. It sounds really good, and while it is partially true, I have to admit, without limit is a little bit overstated because the hardware limits are still there and they are very real. So what happened with entities and the new tech stack, dots in Unity, we were able to push the limits much further than we ever did before. But at some point, we still hit limits, so we always have to be aware of how we implement things, and optimizations are not obsolete. They are still as important as before. So today, we're going to split this talk in three sections. We quickly, at a high level, go over the game architecture, because we are not very conventionally using the Unity components like you might think we do. Another section is about the asset management, where we also do a little bit of custom funkiness. And finally, the simulation, which is a little bit more tied to the ECS part of things, and how at the very high level did we structure our systems and dealt with our debugging pipeline. So let's start with game architecture. So first, the game has been developed with PC and current generation console in mind. I'm not sure. Hello? Can you hear me? Yes. So the game has been developed with PC and current generation console in mind. And currently, we are on Unity 22.3, so pretty recent version. And we keep updating as we release patches. We use a modified version of HDRP. I will get a little bit more in details what kind of modification we're talking about on upcoming slides. And we use entity packages, which is entity, burst, and the collection associated to it, and the mathematics package, which didn't fit in here, but is very important as well. I want to mention we use a new input system. It's not a new input system anymore at this point. I believe you might still already all use it. Anyone using the old input system in this room? We have 2, 3. Don't be shy. Okay, some are still using the old one, and you probably know it comes with some limitation, especially when you want to integrate gamepad. So the new input system has actually been a very good fit for us. So we support both playing with mouse and keyboard or gamepad. And at any point in the game, you can just pick up your gamepad, touch a control, and the UI switch to have the gamepad hints and everything, and you can get back to your keyboard. So it's very convenient. You can kind of decide if you want to go to your sofa for a bit or something like that. So new input system works really nicely. Finally, the UI is quite an interesting aspect and a subject for a completely different talk, but I need to mention about it. We use a third-party library developed by Coherent Labs. The name is GameFace, and it's basically making UI using HTML, JavaScript, and CSS. So it's very close to web development. And what our UI is a big React app, which we can almost run in Chrome as well. So it's very convenient to develop the UI for the game because we can use standard web development tools. We use Chrome to debug the game UI. And the game just ran a JavaScript engine, a V8, the V8 one, same one that Chromium used. And it's been a very good fit for us. So I will talk a little bit also about the systems in a while. And finally, we have several self-made custom packages, which are not very important in themselves, but I have a whole slide about it. The Unity Package Manager, which you all have been involved with at some degree, and some love it, some hate it. For us, it's been really useful. We used it as a separation of what is a package that is part of the game that use game types, and what is a package that in the future we could reuse with another game or just should not belong to the game code. So we don't cluster the game code with all kind of useless if-def that are very hard to get cross-platform to compile properly. So we used the packages in a very traditional way, and we have a combination of built-in and local package. And on top of that, with the assembly definition references, and some changes where we have added the attribute internal visible to, we can have a very clear and clean separation where a platform integration, for example, is implemented in its own package and will only be added to the build if we make a build for that particular platform. So the code remains pretty clean, and we can focus on the game, in the game project, and we can touch the rest outside of the project. So we have a good dependency management when it comes to that, and the Unity Package Manager has been really useful for us because it speeds up development time, compilation time, all kind of those things. So I recommend using a local package if you get the chance. So, but the game architecture itself, we do use one mono behavior. Formerly, you used a lot of them to make a Unity game. With ECS, this whole architecture really goes away, but we still use one to manage the game loop and to manage the initialization and the cleanup of the game. Nowadays, you can use await async paradigm with mono behavior. So we leverage this so that the initialization of the game and the cleanup is asynchronous, so we don't really freeze the game for too long. It still freezes a little bit because not everything can be done like completely smoothly, but it's really helped us to have cleaner code at the cost of little bigger binary. So for PC and console, it's not too big of a deal. And the update loop is pretty standard, so I still will go through it because it's important in the second point. We dispatch the input messages first, and we do a manual word update for the ECS word. So that's why it's interesting. Unity provides a bootstrapper. I think it's still called like this these days. And the bootstrapper pretty much does this whole update for you. So you just register a system and you organize the things. But it did not exist at the time we started to work on the project. And like many other things in this talk, the reason why I say no something is not because it's bad, but it's because it did not exist at the time. And once we had our solution, it didn't always make sense to migrate. Then we take the UI that goes to JavaScript and all the layout is done and everything like that. We have late in the frame, we have a cleanup for the ECS word because some allocators need to be cleaned up every frame. So this is where we do that. And finally, we have a main thread dispatcher that helps us to manage assets When doing any kind of operation on the asset database we use, we get asynchronous callbacks. They can happen on any thread. They are managed threads, but they can happen on any threads. So we need still to use a main thread dispatcher, which is a glorified action queue. And with that, we can just execute things we need on the main thread to update the UI or whatever other assets are being updated into the game. And finally, the platform integration callback, which is just so that you can see your achievements when you actually play well. So when it comes to prefabs and component architecture, I will say right away, whenever I will say prefabs in this talk, I'm not talking about Unity prefabs, just to be clear. We don't use Unity prefabs, and we don't use game object entity conversion either, because it didn't exist at the time. So we kind of came up with something a little bit more custom, but very primitive, so that it stays really simple. So our prefabs are more or less scriptable objects where you have a prefab of a specific type, and then components can be added so that you can have only one unique component type per prefab. The reason for that was to avoid game designer getting confused having 20 same components, which is something that you can achieve with mono behaviors, for example, and as in the past shown to not be always a good practice. So we kind of set these rules, and everything relies on that. This is the only data-driven structures that we have, and all our prefabs, absolutely everything that exists in the game is built on top of that. Prefabs are using OOP, so they are not like, they never really go into ECS itself, so we don't need to optimize them very much. So we still use inheritance to have common ancestors for certain prefabs, so we can find them by type and so forth. So it's still convenient to work with them. And when they get registered to the simulation, they create a representation that is going to be their ECS representation. And it's not necessarily a mirror of what you see here. And here, the personal car, for example, might create 3 different components, and the simulation will deal with them separately. So that allows us to extract the data from the gameplay data that is designer-friendly and turn it into a better packed format that is more optimal for the cache and for ECS operations in general. And one thing I also want to mention, it can be a bit obvious, but it can be also forgotten easily. We use a reverse dependencies between quotes approach to prefabs for scalability. So I can give you a concrete example. If you have a tree and you want to spawn a variation of that tree, the naive logical way would be you have an object, and then you say this is a random tree, and you reference 5 objects that are 5 different variations. And then when they spawn, you pick one of them. We kind of do it the other way around. We have a prefab that is a placeholder, and then the actual tree say, I am a replacement for this particular randomization item. And this allows us to add more content later, which could just make more randomization without really having to patch the game in any way. So it's a small thing that is easy to forget, and we've built all our prefab on top of that, and it's been so easy to work with it. So I recommend this kind of approach if it fits your need. And then one thing about the rendering, I will be fast on it because it's quite a big topic in itself, but HDRP is not completely integrated with entities, and some of you probably faced this problem before. So we had to do quite a lot of local changes to that package. And the terrain, the water, shader graph node, mesh decals, so they wouldn't use projectors. We had to do small changes. They are not really big, but they make merging much more difficult later. And the UI rendering, we needed it to render full resolution when we use DLSS or any other downscaler. So we had to hook up some new rendering paths in HDRP there. And the big one is the light collection from entity worlds. Currently, you kind of need to use a hybrid approach where you kind of pull game objects to collect certain data types. So lights are still use components. They are still in the native side of Unity, so you still need to use them. Cameras kind of have that as well. Audio source, visual effects. These are you can't really work around it, and pulling is usually the way to go. In our case, we can have tens of thousands to hundreds of thousands of lights like in the scene at the same time. So pulling this amount of objects is not efficient and should not be an operation we offload to the main thread because we have better things to do with it. So we changed the HDRP code to pull all our lights directly from our ACS world. And that was quite a big change because we need to pack the data on GPU in a similar way what HDRP does. And that makes it that updates to HDRP are a bit tricky. Then other than that, we don't use entities graphics. Again, for the same reason, it was formerly known as a hybrid renderer. It kind of appeared later, so we already had some sort of solution for it. But at the time, the underlying system that the entities graphics use is a batch renderer group that you may have heard in some other talks earlier and in the keynote as well. So a combination of that API plus a sparse uploader to update the compute data that holds the instance data, we were able to get a very similar approach to what the hybrid renderer does without really having to use it and suffer from the potential changes of such an early package again. And we were also able to optimize better what kind of components we use to render, because we don't need all the information Unity has, because we're not as generic of a game. So we could pack things really nicely. And then other than that, everything's quite standard. We use the normal APIs for our shaders are SRP batcher compatible. And we just have an extra pass of batching, because the way our assets are built, it's a little bit difficult to share materials between different objects. So we actually duplicate a lot of materials in their source, and they reference a template master material, which is a normal Unity material. And when we instantiate them, we check, are they actually, is the result the same material as another one that was already registered, and we merge all of this together. So that makes rendering performance far better. And we have some specialized systems like the notification icons that show on top of buildings. We can have several tens of thousands of them as well. Working with the SRP batcher and entities in there was not exactly ideal, because it's a very specific data structure. So we just use the normal instancing API that is provided by Unity, and graphics that render mesh indirect, and the 10 other variants to it that are available in there. So that's about it for the game architecture in general. And now a little bit about the asset management, because it is also custom. We implemented our custom asset database. It's kind of what Unity asset database is, but it is available at runtime. And we support modding, which is one of our main motivation into doing it that way. So modders need to be able to import and store their assets, and we can't do that in the Unity asset database because it doesn't exist in builds. So we added a simple database, which is a large dictionary of assets, and then we can split that into multiple databases that get populated from different data sources. The game installation folder is the core source that is always needed. And then there's a user folder, some cloud storage like Steam Cloud or Microsoft Connected Storage, and mod subscription also go in their own database in the same way than the rest. And with this database, we can easily index assets. And when subscribing to an asset or when loading an asset, we don't really do anything. And that's why we call them lazy assets. They are just GUID. Until they are used, they are just a GUID. So they are very lightweight. We don't do anything with them. But then when we need to access a particular asset, let's say a texture, we're going to index it by its GUID and load minimal metadata, which will give us, in the case of a texture, the width, the height, the dimension, the graphics format, and all those metadata that we might need to pre-calculate something in the simulation. And then using that GUID system, we are also aware of all the assets which are in the game without actually loading any of it. And with modded content, where if it's like with the first game, after not so long, they already had more assets than we had in the base game, we kind of need a very efficient way to add content without really without hiding it behind a large package where no one knows what's in it. So this was really suitable for that kind of thing, and it allowed us to make a suitable loading API for each of the asset type. And that really enabled us to bring streaming into the picture. The data that we request is only the one that we need. So I can give you an example with geometry. Recasting, for example, may need to know about the geometry of the tessellation of the model, so position and normals. But it might be that it doesn't care about the UVs. So we only want to read mesh and normal from disk at that point. But later, when this geometry is going to be rendered, we actually want to get the UV and other vertex attributes that might be associated to it. So our API just provide a mask, and we can say, load this now. And if it's already loaded, it will only load the data that's missing. So we can quite efficiently use the smallest amount of memory that we can with geometry at least. So yeah, that's one of the reasons it's implemented that way. For a little reference, the some stats about the assets. We have about 8,000 unique geometry that are a combination of multiple meshes. So in practice, we have far more. Most of them are 2 or 3 sub-meshes. So that kind of add up a lot when doing batch rendering. And that's why batch rendering is great. And texture and virtual textures, we have a total of 15,000. Most of our content is in 4K. So this is huge in disk space, and it's also huge in memory. So we had to find a solution for that. And prefabs, which are gameplay prefab, render prefab, what I mentioned earlier, we have over 40,000, and this increases all the time very quickly. And then a bunch of other assets that I just want them written so you know that this is not all, but they are not relevant. They just do what you think they do. So the streaming is kind of the key point there. To handle this amount of data, we need some kind of streaming solution. For geometry, we don't really have a streaming API for vertex buffers, so we went with the traditional way where we just distribute a certain amount of meshes over certain frames, and we track the memory they take, and after a certain amount of time, if they have not been used, we just nuke them from memory so that it makes room for another one. So we have a static memory budget, and if we go over that budget, let's say if somebody creates 500,000 custom assets and the memory can't fit them all, we just replace them by boxes so that the game won't crash. The gameplay will work, but it will look kind of bad. But we're kind of really far from reaching this kind of limit, but it has to work that way for flexibility. With the texture, it was a little bit more complicated. We implemented virtual texturing for it, and we relied on Unity low-level procedural virtual texturing for it. So it's an experimental API that is completely undocumented. So there was a lot of work and collaboration put into that. And what it does, the virtual texturing, there is we pre-bake the texture, we tile them into smaller blocks of textures, so that whenever the camera looks at something, we get feedback of what is the MIP level and what is the area of the texture that is used. So instead of loading the entire texture, we only load the tiles that is visible, or multiple tiles, and the MIP level that is used. So if we see the city from very far away, we'll have the highest MIP for everything, so we use very little amount of memory. But when you get really close, you need 4K resolution, but you only see it on the building that is really close to the camera. So that way we can mitigate the amount of memory that is required. And as the camera moves around, it's constantly streaming that data in and out. So it's quite heavy on the I/O. So there is a lot of packing and stuff happening behind it. But ultimately, the API the Unity provide is just a callback that say, I want to get this region and I want to get this MIP. And this happened to be first compatible with Burst using native structures, and very easy to integrate with jobs because we can use job handlers we can use job handlers to kind of chain our VT request with certain things that need it. So it actually fitted really well within ECS architecture, the system that I will get to very soon. And the async read manager, that is also part of the entities package, or actually part of the native code, but also available with the entities package, has been our go-to to do file access, read only, but this is an API that replaces the C# streams. And that is kind of good because C# streams are not compatible with Burst, but the async read manager is. So not only it's nice to integrate because job handlers make it really easy to chain, but it's also possible to optimize a lot out of it because it can go through Burst. So I have a last slide about the asset management, which is a bit more about the editor tooling. We tried to minimize the amount of tooling work we had to do for the game because with custom asset database and things like that, we could have really gotten stuck making UI that is pretty to manage asset that would have taken forever. So we always went with minimalistic things. So what we ended up with are build scripts, which most games need because there's always a SKU customization you need to do where you need to remove files, add more files, which Unity built-in pipeline doesn't handle. So we have a couple of scripts like that integrates well with our automation. Then we added some system to do integration tests in the game. So every time somebody commits code, when the game compiles, we automatically do smoke test on most of the things we can test. And that's been very useful. But these were like kind of completely outside of the game. And then we had to do the tooling for importing and compressing textures, geometry, animation, all the data that Unity normally does. And those were quite a lot of work, but we still managed to keep a very minimalistic UI so that artists don't get lost in it. And all these tools are available at runtime and are used in the modding pipeline. So that's very convenient that we can have both at the same time. Then debug and validation tool we also had to implement and at many levels. And at the asset level, I have a picture of what a debug scene would look like. In here, you can see that we have a set of assets, not all the assets from the game, but everything that is in the European region. And on the left, you can see that we do have game objects and hierarchy, and this is actually how we can debug if the import was successful, so we can browse through the asset using the traditional mesh renderer, so we can play around, we can experiment changing the materials, changing values, and that way we can figure out, is this looking like it should? And once this looks well in there, we just send it to the batch renderer in the game, and it will look the same. So it's been quite useful to debug. And at the bottom, you can see this very old school window that just lists all our assets, and this is kind of how we track what is in the database, and we don't really have to do anything else with it. So you just wanted to show a bit what this looks like. And on the left, there's just an asset import tool. This is our asset importer. It's literally just a path and a checkbox and a create button. So yes, that's about it for the asset management at this point. And let's continue with the simulation, which is closer to the ECS. So let's get back to what we were trying to achieve, a larger scale simulation. To do so, we leverage DOTS, as I mentioned earlier. And DOTS is a combination of three major systems, which is the C# job system, the entity component system, or entity package, and the burst compiler. We adopted that in 2018, so we started really early, as I also mentioned earlier. And quite quickly, we noticed we were going to manage to push the limits further, like we wanted to accomplish. So we, especially burst, kind of stood out for us. And we don't use IL2CPP on PC because for modding support, it's much more convenient to keep mono and have modders be able to use GIT for the code. So mono is still infamously slower than IL2CPP. So that's where burst actually really came into the picture, where in some cases, bursting code is actually far better than trying to let IL2CPP do something with it. So I have an example about it. I in fact don't have much to say about the burst compiler. It's awesome, it works great, and I really have nothing to complain about. So you have a profiling capture here, which shows a batch manager system that batch culling jobs that normally without burst would take 84 milliseconds. When bursted, exact same scene, exact same code, we get down to under 1 millisecond. That is absolutely insane ratio. And not all the systems do as well, but a lot of systems that are mass heavy are excellent to compile that way. So our recasting also 40 milliseconds without it, 0.5 milliseconds with it. So this slide is really to encourage you, if you don't already burst most of your code, do it, because you can have some real performance gain out of it. In our case, all our jobs are bursted. And in some cases, we also burst some static methods when the data structure is burstable. So if they don't access any classes and all the types are blittable, why not we just add an attribute and then it's faster. So systems, however, do not use burst. And that's one of the things. Nowadays, you can use systems that are burstable, so do it. It just didn't exist at the time again, so we had a lot of system, and it didn't make sense to rewrite everything at that point because we were aware the system cannot be bursted. So we don't actually run any code that is very heavy in the main thread from a job. So turning them into bursts wouldn't really help so much. So we haven't put the effort into doing that. I hope someday we can do it, but it's quite a lot of code, so we'll see. Then about the ECS itself, I will just have a little reminder here where OOP versus ECS stand and why it's good to go with ECS. OOP is formally just you implement an object, you implement the logic on it, and then you derive a lot of classes. It gets really complicated really quickly, and in our case, maybe it's not like that for everyone, but in our company, we very quickly end up in a situation where the relationship between the classes are actually not smart anymore. At first, it seemed good, but they start blurring the line of what should be what. And in the end, it's just a spaghetti of code with dependencies that are very hard to manage. So that's one of the problems that we face with OP, but the other one is the virtual calls performance hit. When you need to call a method on an object a million times, you will actually see the cost of doing a virtual invocation. So we can get rid of it by taking a different approach. So conclusion about OOP, it's just not so scalable, so it's not very suited for large-scale simulation like we wanted. ECS, on the other hand, it's data-oriented. So data is stored in components, and systems just take these components, filter them, and do whatever a system should do on them. So you can actually do volume with that. It's very scalable. It's also clean because you have very clean separation of what is data, what is logic, and finally, because data is separated, you can pack it in a much smarter way. So you can actually be cache friendly in most of your data structure, and you get better performances out of it. And because usually when you want to change one object, you can change millions of them at the same time. Parallelization and batching is actually very suitable for this. So conclusion, ECS good for simulation and OOP not so good, but OOP still has advantages, so we didn't completely remove it from the game. We just use it where it makes sense. So our prefabs, like I mentioned earlier, and our systems, because in some cases, we can subclass systems which have a base implementation, such as debug facilities, UI helpers, and stuff like that. And finally, the multi-threading point of this is this architecture is inherently excellent to multi-thread, and it allows to write scalable code. So with multi-threading comes the problem of race condition, which is one problem that has been very hard to solve in the past. Unity provide a very good tool chain and a very good infrastructure to detect the race condition early on, so you don't end up with all these kind of bugs that you will never reproduce or never solve. So the dependency management help us to do that. It's the job handlers I was talking about earlier, and it's pretty efficient. It's seen a lot of optimization since it started being developed, and it's in a place where it can be used quite large scale. And the safety system, that one is absolutely critical to make sure that you don't, let's say, write in a place that is being read, so the data gets all over the place and you get actually crashes as well. So Skylines II code base is about more than 700 system, more than 900 component data, over 1,000 jobs. And in the case of a city which has 100,000 citizens, we have 1,700 non-empty archetypes and over 500,000 entities that are actually all being updated every frame. Sometimes distributed, but still quite a lot. And that scales up as the city grows bigger. So I think ability to have that many entities is a good demonstration that the technology was a good choice for the game. And in Skylines I, I think a 1 million citizen city had less entities being updated than this. So we really were scaled up in the title thanks to the dot pipeline. Then let's just have a little look on how the systems and the components go. So starting with the systems, I mentioned already all the systems are managed. So there is a downside to that. We do reference systems between each other. So we can have very deep trees of references. And we thought it would be a problem, but in the end it wasn't, because we only do it once when the game starts. It takes under 2 seconds, so it's not the end of the world. And after that, we just have those references. They never change. So that's one of the reasons we didn't move toward the entities-based system, the iSystem interface. But again, this was done because it didn't exist. So we still would prefer to use iSystem if we could. And the UI is kind of an interesting aspect. UI is also separated from the game, just like all the data-driven development instructed us to do and taught us to improve our ways. We also split the UI logic completely from the game logic. So we have dedicated systems, dedicated ECS systems that will query and pull the data that they need and cache those so that they can be updated to the UI on the next frame or back to the main thread in the main thread, depending what time they are being updated. And at the end of the day, we just have a data binding layer so that all the C# data is passed to the UI, because we need a way to give all that data to the JavaScript engine. So we have a data binding layer that is used into the systems themselves. And when a value has changed, we just send it over to JavaScript, and we let JavaScript deal with all the updating of the UI. If that value has changed, then React will take care of finding which components in the tree do I have to re-render, and we can get very optimal UI rendering that way. Plus SVG support, which is actually nice to have inline SVG. We have a lot of graphs, so this is quite important. And then for the components, the guideline that was given to all our programmers is make them cache-friendly whenever you can, and memory-friendly as well, because when you handle this volume of entities, it takes a lot of RAM, and RAM is a limited resource, so we try to pack data as well as we can. And we did quite good with the implementation we have, but later was introduced something called aspects, which kind of could help us to get better optimization by splitting a component data into separate blocks that can be used separately. But aspects, unfortunately, was quite a bit of a different architecture, and it's one of the things we have in our to-do list in the future optimization. We will try to bring them into the game. But they seem very nice, at least. So how we put all this together, and how did we manage to work with ECS since it launched in preview, where the API was very light and very experimental. So we kind of did it by not using high-level APIs. So all the lambdas for each, all those like helpers that are super nice to use and reduce boilerplates, they are great. And they are great when they are stable and they don't change anymore. But if they don't seem to be final, it's better not to commit to them, because they come with arbitrary limitation. Like in some cases, it was we couldn't pass more than a certain amount of type handle to a certain job. So we just ended up going with everything implements iJob parallel 4, and other derivative of it. And like 95, maybe more % of our code, our jobs use iJob chunk to run the multi-threaded logic. And the ECS system, to schedule our ECS system, is what I talked about in the update loop. I said we do a manual update, and now I can explain what does that really mean. Is we have an update system in the ECS world, which responsibility is to register all the systems that will run into the simulation. And we can register a new system saying update at or update after, and we can basically just lay out the flow of the system in the simulation based on this definition. And we have multiple update phases, which are arbitrary concepts that are synchronization points, so that when we touch the ECS world, we need to know at the end of a modification, this data is ready to be used in the next one. And for that, we use entity command buffers quite heavily, but we realize with the entity command buffer, it's very easy to schedule it in the wrong place, and without really noticing it, because very often if you have an ECB that runs too early, it might not have any side effects. And you're like, okay, everything is great, I've finished my job. And then it starts randomly causing some crash. It's very similar what a race condition would do, except that it doesn't crash, it just does some really weird stuff. And we realized this mistake happened too often, so we just wrapped the entity command buffer into a safe equivalent to it, and we create barriers between each modification. So the update system will take a parameter when you register a system saying, I will be updated during this phase. And that way we guarantee that if we need to update a bunch of nodes before we read something from it, we have this modification step. And we have an arbitrary amount. Like I think we have 5 main modifications with A and B for some of those, but this is what we needed, but there is no actual limitation to that approach. You can go very complex with this. So yeah, that's about it. I mean, I want to point out one more thing. I like to praise ECS because it is good. It is an amazing piece of tech and it works well. But not everything belongs in ECS. But everything belongs in jobs or in the job system. So what's important to know is because you write ECS code doesn't mean everything has to be ECS. And when you decide not to go ECS, that doesn't mean you have to go back to mono behavior and the traditional thing. You can allocate a large persistent buffer, for example, it depends what you're trying to do, but you can allocate a more old school way where you store your data structure yourself and do your pooling yourself. And the advantage in that is in system where you do not need the flexibility of components, you do not need the overhead of them either. So pathfinding, for example, is a great reference on how it is not necessarily suitable for entities. And flow simulations, electricity, for example, it's very similar to pathfinding in terms of node dispatch. So in cases like that, we just want to, we can't really batch that. By nature, the data structure is not very batchable. So instead of going all the way ECS in there, we just minimize that, store the data outside of ECS, but operate on it alongside the ECS updates. And that allows us to do some pretty nice optimization in places and also kind of step over certain limitation ECS might create. So it's very good to know that. But when you do that, also always work with native collection, unmanaged structure, because you still want all that code to be bursted. I will say the bursting so many times today. So yeah, and I have kind of a last topic about the debugging and profiling of multi-threaded code on ECS. You can debug a multi-threaded code by putting breakpoint, but very often it's not that useful. So what you need to debug multi-threaded code is a very good visualization tool. So you can actually see the data and not breakpoint into it, because you can see it all in one place and you can see how it relates in, next to each other. So in the whole Skylines II title, we have made a lot of debugging system, and their purpose is only to show debugging information. So just like UI systems, they are standalone. They query the data they need, and they don't interact with the game world unless you instantiate them like explicitly by going to the debug menu. So we pay no overhead to it in a normal game. And so we just built a lot of those dedicated system, and I will show you a few screenshots soon. And the debug log, that's actually a funny one, but as always, debug log is very useful. And in cases like that, we have actually wrapped some debug log, which you can call pretty much from anywhere, anytime in Unity. We wrapped it into some conditional attributes so that they won't compile into the game. But we can keep them into the code base so that these areas where we have code that breaks pretty often, and already 3 other programmers have gone through the process of debugging, they still have the leftover debug logs that you can just unfilter, and then you start getting it in the editor, and you can find your bugs way quicker that way. And the tools provided by Unity, namely the Unity Profiler and the Entities Inspector and the Search too, are very, very good tools, especially the Unity Profiler. So profiling is very important. You should always actually profile your ECS code, because it's not only about is it fast enough, it's also about is it scheduled well. And the only way to really see what's going on in a frame is to see in a profiler what is the thread usage when all the jobs are running during that frame. And the profiler really gives you an insight on whether or not you are scheduling your job smartly. So very often you will notice that you have some code that has no dependency to anything, that is just blocking a schedule. So main thread is just blocking. All the worker threads are just waiting, being bored like crazy. And then you realize that, wait, I can just move this dependency here because it's not actually a real dependency. And suddenly you have all the jobs that could, after that execute at the same time. And suddenly you have 2 milliseconds or something saved. So this is a common mistake. We had so many places, and we still find at this date some places where it happens. After a year through the launch, we still are optimizing some of these not ideal dependency management. So working with the profiler is very important, not just to see that your code is fast, but also that you're organizing it well when it comes to job dependencies. And this is more of a funny story, but sometimes, I said earlier, be careful when touching a package because it can be a lot of work, but sometimes a small modification can make a world of a difference. In this case, we always have this case that when we select an object in the world, we actually want to see its entity and something related to it. Finding the entity always through the search, because we have like hundreds of thousands of them, is kind of awkward. And while the search tools are good, it still takes time. So we just made it that in editor, when you select in the game view a building, we just use the entity selection proxy to actually put it into the inspector. And because entity references are links, if you have any understanding about what is the layout of your the component data, you can kind of browse really quickly to the data you need. So you can actually get all the data you want to see a few clicks away. And that has been the most used tool, debugging tool that we have in the game. And all the programmers touching ECS pretty much always start from there before trying to do anything else. So small change can make big difference as well. And maybe I will mention to Unity, this could be a public API. So yeah, here were some screenshots as promised, so you understand better what I mean with visualizations. You can see on the left there is a hefty amount of tabs, which are all different type of debug data that we can show into the game, and then all the debug systems that we can turn on or off. And it's like, there is not much to say. It's just to show this is the kind of data we visualize, and this really helps us to see if there is a bug, because if anything is incoherent, we will know it right away. And I have another screenshot to show the lane debugging, how it works, so we can very quickly preview what happens when, where can vehicles to do U-turn and things like that. So this really helps us to see if we screwed something up in the data structures. And another one about the land value, it's basically a cell representation. And as we run system, we can see those change in real time, so we can see if there is a bug. And last one about the pathfinding that basically show all the connected areas. Also pretty critical, because without visualization, debugging this kind of thing would be almost impossible. And I'm going to wrap up my talk now with the development challenges. I need to mention it because it's been a long process to update the engine. So we started from Unity 2017 to 2022, from HDRP4 to HDRP14, and from entities 0012 to entities 1.16. So we've seen a lot of iteration to each of these packages. And as an early adopter, we have faced some problems. And most of them we were able to solve by kind of relearning how to do things better if something had changed. But sometimes there are problems that cannot be solved by working around. And then you have to talk to Unity. For example, we had a long-running job problem where pathfinding is supposed to run jobs over multiple frames. So a pathfinding job can easily take 400 milliseconds, and it's okay, it's designed to be like that. But by default, the job system will try to use the main thread to steal jobs so that it can, utilize. If the main thread is free, why not use it for something? It makes sense. But with a long-running job, it doesn't, because if the main thread actually pick up a 400 millisecond job, you start getting a lot of stutter, and you're like, what's going on? And at the end of the day, we managed to talk with Unity and came to the solution that for this game, job stealing is just not a good idea. The main thread is already busy doing so many things. We're not really losing by not stealing job on it. So they just expose the boot config parameters that allowed us to turn off job stealing on the main thread, and problem was solved. Rewriting the path funny to be distributed over time would have made no sense whatsoever. So this was the right way to go. So I will conclude my talk with a reminder. When you write ECS code, be cautious for what belongs to ECS and what doesn't. I will give you a quick example there. You wouldn't necessarily want to represent an image by making each pixel an entity, for example. That you could do it, but it doesn't necessarily make sense unless your gameplay is built on top of that. The burst code whenever you can. I will repeat it all evening, by the way, so you want. If you talk to me tonight, I will say it also many times. And jobify everything you can. That's a very important thing. But also remember, there is a cost to just jobifying. So if you go too atomic, if you make very small operation that doesn't benefit from being multi-threaded, you will end up that the overhead of scheduling all this job will outweigh the performance gain you get from multi-threaded. So again, look at the profiler every time you make a decision. And then a reminder of what I just said, be careful of a long-running job blocking the main thread, but also main thread blocking scheduling of worker jobs. And that concludes my talk for today. We will go into the sunset with a chemtrail chemical advertisement. And I think we still have about 9 minutes for questions. So